Greetings. In this example, I will talk about this object with a mass of 2 kilograms. And therefore, because we're talking about Earth and there's gravitational acceleration at 10 meters per second square or 10 newtons per kilogram, the wave force that's pulling it down will be equal to 20 newtons. Now, will also be a force, especially from this string. Somebody can be pulling it up with a hand or a machine can be pulling it up. That will be counteracting this force, therefore it first of all doesn't fall, and actually it even goes up at the constant acceleration of 1 meter per second squared. In other words, 1 meter times second to the minus 2 power. Now, how to calculate what the tension force of this string that's pulling up the object at the same time, like in opposite direction, the wave force is pulling it down. What force does it have in newtons, just like here? That is determinable by the realization that the net force, and I'm only talking about all vertical forces, no other forces. I'm summing up all forces, but I'm talking about just vertical forces in the diagram, and when talking about net force, it's all the forces together, but because I'm only talking about vertical forces, the F net, I'm talking about just the net force of all the vertical forces, and those are, in this primitive example, the only ones that really affect this entire example. So, the two forces are the wave force and the tension force. The tension force is counteracting the wave force, just like the wave force is counteracting the tension force. And usually you might be faced with this being Ft minus Fw, with the minus there. But one can also just use a plus, and I'll explain how that works in a second. Just keep the realization that when a force is going up, I will say this of magnitude that is plus, it will have a plus sign from it. If it's going down, it will have a minus sign. That's the idea here. So, I know that F net is equal to Fw. And Fw, how was it calculated? It was calculated as m times g. Because g is 10 newtons per kilogram. For each kilogram of mass, there's 10 newtons going down, pushing it down because of, or pulling it down because of gravitational force acting on it, creating a wave force. Alright? So that's mg, because this is the constant of acceleration on Earth's surface, around it, approximately. And then, so I can just write mg here. But what I will talk about is actually the wave force is not 20 newtons, but it's minus 20 newtons. Because as I said, when something is going down, and that's the way I will bring in the minus here, although usually there's already minus in this formula. But in this case, the little bit difference is that the wave force, it's not 20 newtons, but it's minus 20 newtons. Why? Because it's going down. So it's minus mg, alright? M is still 2 and g is still 10. But I put the minus in front of it. So minus mg will happen here as well. And therefore the thing will be just the same as if I wrote Ft minus Fw right in the beginning. But I can do it this way, that instead of saying minus Ft and then Ft being minus Fw and then Fw being mg, I can just say plus Fw, this one, the wave force, and the Fw will actually be minus mg, already defined as follows. And then to that I add the force, the tension force, and that will be something which I will determine. I don't know that yet. So, how to calculate this is to realize that the force is equal to mass times acceleration. And the overall acceleration of this motion is up by 1 meter per second squared. That means when I'm talking about the net force, it will be m times a. It will be m times a. It won't be the m times g. G is a different one. It was only calculated, it was only used to determine this force of 20 newtons, that the wave force going down. It's the acceleration of Earth, but it has right now, in this particular case, nothing to do with the fact that the acceleration of this entire system is 1 meter per second up. So, m times a is the net force. So all forces together will end up being equal to m times a, where a is the acceleration of the entire system. Although there is some acceleration of gravity going towards the object, pulling it down, there's a final net force that will actually have an acceleration of 1 meter per second squared. Therefore, the F net, which is the final force of all added up all together, cancelling out each other and so on, is m times a. And that will be equal to minus mg, because mg is the one pulling it down, plus the tension force which we are looking for. So now adding mg to both sides, finally it yields ma plus mg. And from this, I can just determine very simply that Ft is equal to, I just rewrite it once again, F tension, right? So when it's pulled down, but at the same time it's pulled up, the final tension force will be equal to the mass of the object on which all this is acted times A plus G. It will be times not only the gravitational acceleration down, but it will be increased by what the final acceleration of the system's movement is. Alright, so when you have something that's pulled down by gravitational force and gravitational acceleration of 10 meters per second square, but the thing is moving with the net force, acting, the net force creating the scenario, the case that actually the entire system is moving upwards in the opposite direction to the gravitational acceleration at 2 meters per second square, then to calculate the magnitude of the tension force that's counteracting the wave force, you will use m times a, but a will be extended from just g to a plus g. That means that if there was 2 meters per second here, instead of m times 10, it will be n times 10 plus 2. That's the idea. But this is just a side note that one can derive from it, but not necessary for the calculation. So to plug in the things that we have, finally to get the tension, well, I can just reuse the ma plus mg. That's probably simple when one first sees it. It doesn't really matter, but it might be simple when one first sees it. Well, the force of tension ends up being ma plus mg, where m is 2, so it's 2 times 1. That's the final acceleration of the next situation, and then plus, again, m, still the same object, no other m, and g is 10. All that in newtons. I avoided the units here and just put the newtons unit at the end. And that ends up giving 22 newtons. Alright? So, by all of this, I calculated that the tension force pulling up, counteracting the wave at 20 newtons will be equal to 22 newtons.